Hello, students. Welcome back and good morning. Today, we are going to take our lecture uh, on a very important aspect of this course, that is electric field and electric potential. Okay. In our previous lecture, we focused mainly on Coulomb's law and the superposition principle, right? We look at how charges exert forces directly on each other across empty space. But this is not enough. Just taking the idea of action at a distance is not sufficient. So we need to know, how does a charge know that another charge is closer to it? Or how does a charge know that a charge is there to push or to pull on it? So this is very important area that we are going to dwell much as for today. So to solve this problem, we introduce a unifying model called electric field. Okay, electric field. So if we look at the slides, we are going to explore how space itself is modified by the presence of charge. We will define electric field, link it directly to the concept of voltage or electric potential, and then master one of the most very important tools in classical electromagnetism, that is Gauss's law. Okay, so for today, let's start with the electric fields and potentials. Okay, you can imagine or think of an electric field as a modification of space. Okay, just imagine that. So any charge creates electric fields around itself. So if we bring a very small positive test charge Q naught into that space, it feels what? Or it experiences a pulse. So what this is telling us is that mathematically we can define electric field vector E at any point as the force experienced by that positive test charge per unit charge. So that is why we have this relation, E, which is equals to F over Q naught, where Q naught is what? A small test charge within that space. All right. So because force is measured in Newton, charge is in coulombs. Okay. The SI unit for electric field can be referred as newtons per coulomb, or as we can see later, maybe we can say volts per meter. Okay, so these are the SI units for this relation. So that is why newtons per coulomb or volts per meter. So this is very important because the direction of E is defined by the direction of the poles on a positive test charge. So if you put a positive charge in an electric field, it moves with the electric. It moves with the fields. Okay. If you put a negative charge in, it moves opposite to that field. So for a single point charge Q, Coulomb's law gives us a very clean formula for the fields at a distance r. That is the relation you can see now. Field due to a point charge Q. So the formula can be written as E, which is equals to 1 over 4 epsilon naught Q over R squared, R cup. All right, here the R cup is a unit radial vector pointing outwards. Okay, yeah, pointing outwards, from the charge, as you can see from the diagram, showing the field lines radiating symmetrically outwards from our positive charge. Okay, so this is very interesting. So in this case, before we move to potential, let's look at four rules or some guiding rules if you are trying to understand field lines. Okay, because it's not just drawing the radial distribution with the arrows. No, you have to understand the rules that you can apply before maybe taking a diagram or drawing these field lines. Number one, the fields originate from the positive charge and terminate on negative charge. You have to take note of. In the case of electric field, the field lines originate from positive charge and terminate to a negative charge. Number two, they never form closed loops. So this is unique property in the case of electrostatic fields. Okay, you remember in the magnetism, the lines are forming a closed loop, but in the case of electric field, they never form a closed loop. Okay. Number three, the density of the line is proportional to the field strength. Okay, the density of the line is proportional to a field strength. Where lines are packed tightly together, the field is intense within that region. Okay, so this is very important, and you have to take note of these golden rules before taking care of any diagram related to the electric fields. Okay, now let's talk about electric potential. As we all know, electric potential, we are referring to voltage specifically with a V capital, representing the electric potential. So in this case, if the electric field is electrostatic equivalent of pulse, electric potential is the electrostatic equivalent of height, or we can call it like just an altitude in the case of gravitational field. So it tells us about energy. Okay, so by definition, the electric potential V at a point is the electric potential energy U per unit charge. So that is how we come across this relation. As you can see, B is equals to U over Q naught. Okay, where V is the electric potential, U is the electric potential energy on a test charge or a point charge. So we measure this in volts, where 1 volt is equivalent to 1 joule per coulomb. Okay, so for a single point charge Q, the potential at a distance R is V, which is equals to 1 over 4 pi epsilon naught Q over R. Okay, take note of something here. The electric field formula has R square from here. Okay, you can see, but here we have only R as the denominator. Okay, so the potential formula has has a denominator, and in this case is what? A scalar, no vectors. So the direction is just telling you a simple number. All right, this is important. You have to identify these differences. Yeah, in the denominator, this has a simple R in the case of electric fields, while in the electric potential will have R squared. Okay, in the form of a scalar. There is no vector here, no direction. Okay, so one important thing that I want to mention here is that how are these two concepts connected? I mean, electric field and electric potential. Okay, so mathematical point that combine this E and V is what we are going to see how this relation relationship came up. Okay, so the electric field is the spatial rate of change or gradients of the electric potential. So mathematically, we write this using the gradient operator. Okay, so E is equals to minus the del operator V. Okay, so in our standard 3D Cartesian coordinates, this can be break down into spatial derivatives, as you can see from this equation, using what? The idea in the Cartesian coordinates. Okay, Ex is equals to minus dv dx, Ey is equals to minus dv dy, Ez is equals to dB dz. So the negative sign here is highly profound. Why? Because it tells us the electric fields, it tells us that electric fields lines always point in the direction of decreasing electric potential. Take note of this. Okay? The negative sign here in the in this formulation here is telling us that electric field lines always point in the direction of decreasing electric potential. Okay, so if we want to find the potential difference, for instance, between a point or between 2 points, let's say A and B, we simply integrate the electric fields along the path between these points. Okay, that is why you have this relation. So if we want to write it in this form, what does it telling us is that here we have a concern here. You know, they call out on the concentric cycle, as you can see from the diagram here. Okay, these lines or the dotted blue lines here are what we call the equipotential surface. Equipotential what surface? These lines, the radial blue lines within the cycle, the charge here is what? Equipotential surface. This within that space is what we refer as equipotential surface. So now you can imagine it as just like a contour lines on a topographic map, which represent lines of constant altitude. Okay, equipotential surfaces are regions where the voltage remains completely constant. So this is important. So because of this, the electric field vector E is always perpendicular to the equipotential surface at a very single point. Always perpendicular, okay, to equipotential surface, as we mentioned. So you have to take note of this. Okay. So let me quickly move to the right side of my slides. That is the green area here. Now, if you look at this side or the green side of the slide, there is a theory called the Gauss law. Okay. Sometimes calculating electric field using Coulomb's law and superposition is somehow a very painful exercise. Yes, because of the integration that involved is highly tedious because of that integration. So Gauss law gives us a very simple shortcut that we can use or that we can apply when we have a highly symmetric distribution of charge. Okay, so what this law is telling us is that Gauss law states that the total electric flux through any enclosed or through any closed surface is directly proportional to the net charge enclosed within that surface. Okay, yes, the total electric flux through any closed, flux, electric flux are just field lines like magnetic flux, as we have mentioned previously. So the total field lines in terms of electric flux through any closed surface is proportional or directly proportional to the net charge enclosed by that surface. Okay, so we have this relation. You can see now the formula. This is the direct Gauss law, and this is applicable to when we are going to talk about the Maxwell equation. It's referring to the first set of equation itemized by the Maxwell in his own interpretations in the case of electromagnetic theory. So here you can see that the integral sign have a cycle here has been cycled. So the cycle on the integral is nothing but to remind us that we must integrate over a completely closed boundary, okay, which we call a Gaussian surface. Okay, look at three classic geometries here, where we have the Gauss law and where we apply the physical geometries in the case of Gauss' idea in terms of his law, and make some calculations related to the electric fields. Okay, because dealing with one set of relation may be somehow a very trivial exercise almost. So what we are doing, we have to use this physical some classical ideas to treat this kind of geometries. Okay, so in the case number one, we have a point charge in a form of normal spherical symmetry. Okay, spherical symmetry, a point charge at the center. As you can see, we have a relation here. Okay, so what is it? What does it telling us? Is that imagine a single positive point charge Q, and we want to find electric field at a distance r. Okay, at a distance r. So we choose a spherical Gaussian surface of radius r centered on the charge. So because of the spherical symmetry, the electric field E must point radially outwards, making it parallel to our surface area vector dl. Parallel what? Surface area dl. Sorry, dA here. So by making this idea everywhere within the cycle, the magnitude E is therefore a constant across the entire sphere. So here, the left side of this equation can now be written in a form of E integral dA, okay, which is equals to E into 4 pi r squared, which is equals to Q over epsilon naught. This is the relation. So we can integrate in this form and obtain to simplify this problem. So isolating E, we can have a relation E which is equals to 1 over 4 pi epsilon naught r squared over Q if we isolate E. Okay, so this is it looks we can just drive Coulomb's law directly from the Gauss law into a simple lines of algebra. Now the second case is we have an infinite line charge in a form of a cylindrical shape. So what if we have an infinitely long wire, a linear charge density of lambda relation, which is the charge per unit length? We can express it in this form, similar to the way we solved the first case. So we can isolate our E to be lambda over 2 pi epsilon naught r. Okay, why? Because the electric field points radially outwards, from the wire, passing only through the curved side of our cylinder. So in this case, no flux passing or passes through the flat ends of our what? Of our shape, that is the cylindrical shape. All right. So here the mathematical relation has been given as I mentioned. So L is the length. This L is the length that cancels out on both sides. That cancels out on both sides are leaving us with only this expression. So L cancel L, and we have this expression. So this tells us that the electric field of a line charge drops up only as 1 over r instead of 1 over r square of a point charge. Okay, yes. So take note of this. And the last case, very quickly, is the case of infinite charge plane sheets. Here we have infinite charge plane sheets, surface charge density, in other words. Okay, so here we can use ideas of a cylindrical or box-shaped Gaussian. Okay, because we are imagining a non-conducting sheet carrying a uniform surface charge density rho. Okay, so by using this idea, the electric field points straight outward parallel to the flat end of the sheet or a cylinder, just like a previous case. So since the field emerges from both the top and the bottom faces of the sheet, the total active area is now considered to be 2A. Okay, so the Gauss law gives us a relation 2EA, which is equals to rho A over epsilon naught. Okay, so someone would write it in a different form as 2EA, which is equals to Q enclosed over this relation over epsilon naught, which is equals to this stem. Okay, stem. Take note of this. So the area A, this A, cancel out just like the length in the previous case. So A will go with A, and we are now left with E, which is equals to rho over 2 epsilon naught. Okay, so take note of something here. There is no R in the entire expression here. Why? Because the electric field near an infinite sheet of charge is completely uniform. It does not change with the distance. So that is why here in our last formula, we doesn't have R here. Okay, so take note of this. So note, you choose Gaussian surface that match the symmetry of the charge distribution in this case. So very quickly to wrap up this lecture for today, I want you to remember some important points here. Number one, use a spare for spherical charges or point charges. Number two, use a cylinder for lines, wires, or coaxial cables. 3, use a box or pillbox for that in case of a flat sheets and plates. So this symmetrical changes has a different mathematical expression that match their symmetry. Okay, so this is important, and using some basic algebra it has been resolved, and you can apply this to spare, you can apply to a sheet, you can apply to a normal cylinder, as you can see. All right, so thank you very much for today. We have taken much of our time. If there is any question related to this, you can send it through my contacts, or even in the group you can just send it so that we can address area of difficulty. Thank you very much for today. Have a nice day. Bye bye.